Welcome to Lecture 4.4, Finitely Generated Abelian Groups. This lecture immediately follows the one on the fundamental homomorphism theorem, and in doing so, it is a little bit non-standard, because there are four classic theorems in group theory that are collectively known as the isomorphism theorems, with the fundamental homomorphism theorem being the first of these. So it is probably more common to follow that with the second, third, and fourth isomorphism theorems. However, in our previous lecture, we finished with an application of the fundamental homomorphism theorem to the group of integers and quotients of that, which gave us cyclic groups. And this is a natural extension of that example application, so we will do this first before continuing on to the rest of the isomorphism theorems. We've seen that some cyclic groups can be expressed as a direct product of smaller cyclic groups, and others cannot. For example, below are two ways to lay out the Cayley diagram of Z6 so the direct product structure is obvious. Namely, Z6 is secretly isomorphic to Z3 cross Z2. And this is not at all clear if we use a Cayley diagram for Z6 using the canonical generator of 1, and it looks like a big circle of length 6. However, the group Z8 cannot be written as a direct product of smaller cyclic groups. No matter how we draw the Cayley graph, there must be an element or an arrow of order 8. Now let me ask you why that is. It's not easy and it should not be obvious, but it's worth thinking about. We will answer the question of when Zn cross Zm is actually isomorphic to Znm, like it is for Z6, but it is not for Z8. And in doing so, we will completely classify all finite abelian groups. Here is the answer to that question. Znm is isomorphic to the direct product Zn cross Zm if and only if the greatest common divisor of n and m, or the GCD, is equal to 1. And that just means that these numbers are relatively prime. I will sketch the proof of this, and it will have enough content that you should be able to fill in the details and write up a formal proof if you so choose. Before we begin, let me remind you that because this is an if and only if proof, that we actually have to prove two things. We first need to assume that Znm is isomorphic to Zn cross Zm, and from there prove that the GCD of n and m is equal to 1. And then conversely, we have to assume that the GCD of n and m is equal to 1, and we have to prove that Znm is isomorphic to Zn cross Zm. We'll do the reverse direction first. Let's suppose that the GCD of n and m is equal to 1. We claim that the element 1, 1 in Zn cross Zm has order nm. If we can show this, then this group, which we know has size nm, must be cyclic because it contains an element whose order is equal to the order of the group. Let's start with the element 1, 1, and this generates 2, 2, 3, 3, 4, 4, and so forth. And at some point there will be a kk, which is going to be equal to 0, 0 in Zn cross Zm. And this is only going to happen if k is a multiple of both n and m. So the order of this element is the smallest k, such that kk is equal to 0, 0 in Zn cross Zm. Naturally, this happens if and only if n divides k and m divides k. In other words, k is a multiple of both. Moreover, k is the smallest such multiple. So k is the least common multiple of n and m, but because these things are relatively prime, in other words, they have GCD1, it's a basic fact that the LCM of n and m is n times m. Perhaps you remember this from your Intro to Proofs class. It's a basic property in number theory. So that proves the reverse direction. We have confirmed that this group is indeed cyclic of order nm. The following picture illustrates this using the Cayley diagram in the group Z4 cross Z3, which is secretly isomorphic to Z12 because it is cyclic. And we can see it is cyclic because 1, 1 is a generator. Let's try this out. Let's start at 0, 0. Let's go to 1, 1, and then keep adding 1, 1 to itself. That brings us to 2, 2, to 3, 3, which really is up here is 3, 0, because second factor is a Z3. Then add 1, 1 to it, that brings us there, but that wraps around to 0, 1. Then adding 1, 1 again gets us there. And 1, 1 again gets us up there. And then 1, 1 gets us there. And that gets us there. And then we get to 1, 1 gets there and up there. 1, 1, 1, 1, and 1, 1 gets you back there. And that is the 12th step. And here, notice that I have used a blue arrow for this 1, 1. And I don't want to confuse that with this light blue arrow that I've used for 0, 1. This is a third generator in addition to 1, 0 and 0, 1. And of the three, it's the only generator that is actually a generator of the entire group because the group is cyclic. Let's prove the forward direction now. So let's suppose that Zn cross Zm is indeed cyclic of order Nm. In that case, this group must have an element AB of order Nm. For convenience, we will switch to multiplicative notation and denote our cyclic groups by Cn instead of Zn. And when I draw the Cayley diagram, it will be clear why we're doing this. Clearly, Cn is generated by A, and Cm is generated by B. And that's because AB generates Cn cross Cm. Let's look at a Cayley diagram for Cn cross Cm. So over here, and I'm arranging everything in a grid, and I'm using generators E, B and A, E, which arise from the two generators A and B of Cn and Cm. And another reason why I think it's nice to use multiplicative notation is by looking at this node, A, B to the m minus 1, well, in additive notation, that would have been A, m minus 1 times B. And there's no way that would have fit in a small node like this. Also, I think the multiplicative notation is just more natural in this setting. Now, let's look at the element AB and look at the order of that. So AB is right here in the Cayley diagram. It's what you get when you do red-blue or equivalently blue-red. And let's keep adding this thing to itself. And eventually, if we do that, we will get back to EE, the identity element. So when you add AB to itself, you increase your row count and your column count by 1 every time. So when you keep doing that and you end up back at the first row and the first column, then the number of steps must be a multiple of the number of rows, which is n, and a multiple of m, which is the number of columns. By definition, the order is the least common multiple of n and m because it's the fewest number of times that it takes to add AB to itself to get back to the identity. However, we chose A, B to be a particular element of order Nm. So this order is Nm, therefore the least common multiple of Nm has to be Mn. And another basic number theory fact that you've probably seen in an earlier class is that that can only happen when the GCD of n and m is 1. In other words, when n and m are relatively prime. And that's the end of the proof. Recall the forward direction, we were trying to prove that the GCD of n and m was indeed equal to 1. At last, we are ready for the fundamental theorem of finite abelian groups, in which we will classify all finite abelian groups up to isomorphism. Now there are two very different but equivalent ways that this theorem is typically presented, and most books or resources will show only one of these and not the other. However, I will show you both, and note that we have learned enough about cyclic groups to understand why these are equivalent. So the first form of this theorem is the classification by so-called prime powers. And it says every finite abelian group A is isomorphic to a direct product of cyclic groups. Actually, both of the versions of the theorem say this. But this version does it by prime powers, which means that for some integers n1 up to nm, A is a direct product of cyclic groups Zn1 cross Zn2 all the way up to Znm, where each ni is a prime power, meaning ni equals pi to the di, where pi is prime and di is a natural number, so like 1, 2, 3, and so on. The proof of this is more advanced, and while it is at the undergraduate level, we don't yet have the tools to do it, and I'm not going to go off on a huge tangent to develop those tools just to prove this. I am much more interested in having you understand and utilize this result and compare the two different forms of this theorem. Let's do an example. Up to isomorphism, there are 6 abelian groups of order 200. And by the way, 200 is factored in primes as 2 cubed times 5 squared. Z8 cross Z25, both of these are prime powers. Z8 cross Z5 cross Z5, again, all of these are prime powers, 8, 5, and 5. Z2 cross Z4 cross Z25. Z2 cross Z4 cross Z5 cross Z5. Z2 cross Z2 cross Z2 cross Z25. And finally, Z2 cross Z2 cross Z2 cross Z5 cross Z5. So we actually know that these 6 groups are non-isomorphic. And I've arranged them so these 3 on the left have a Z25 factor, and these 3 on the right have a Z5 cross Z5 factor. So let's look at the left 3, and notice that Z8 we know is not isomorphic to Z2 cross Z4. We learned that a few slides ago. Z8 has an element of order 8, and Z2 cross Z4 does not. Similarly, Z4 is not isomorphic to Z2 cross Z2. So Z2 cross Z4 cannot be isomorphic to Z2 cross Z2 cross Z2. This group has an element of order 4 and this one does not. And similarly over here you can do the same analysis. So these groups are truly distinct, and this theorem says this is all there are. There are no other weird fancy abelian groups of order 200. If you have one in front of you, it has to be isomorphic to one of these 6. So one thing that you may be asking is, well, what about the cyclic group Z200? So Z200, which one of these is that isomorphic to? Well, do you see it? I claim it's this one right here. 8 and 25 are relatively prime. In other words, the GCD is equal to 1. So this thing here, by what we proved in the previous slide, has to be equal to Z200. And then you may ask similar questions about other groups. What about Z100 cross Z2? That's a group of order 200, so it has to be isomorphic to to one of these, well, which one? So I encourage you to pause the lecture and see if you can figure out which one this is isomorphic to. And when you finish that, we will show you the other version of the classification theorem which will answer that question. Welcome back if you did indeed take a break. Now, finite abelian groups can also be classified by things called their elementary divisors, as opposed to prime powers. The mysterious terminology comes from the theory of modules, which is an advanced graduate level topic. The classification theorem by elementary divisors starts out just like the one by prime powers. Every finite abelian group A is isomorphic to a direct product of cyclic groups, but the only difference is how you describe the cyclic groups. In this case, you have some integers k1 up to km, so A, as before, is isomorphic to zk1 cross zk2 up to zkm, but now each ki is a multiple of the next ki plus 1. Let's do an example. Up to isomorphism, as we know, there are 6 abelian groups of order 200. Let's do them by prime powers and by elementary divisors. And I claim that we actually know enough to construct this decomposition so that ki is automatically a multiple of ki plus 1, which is how you do it by elementary divisors. So let's do it here first. So z8 cross z25, 8 and 25 are co-prime, so we can combine those and say this is isomorphic to z200. Notice that I've made this purple because it has factors from both p equals 2, the red term, and p equals 5, the blue term. Next, z4 cross z2 cross z25. Here's what we're going to do. We're going to take the largest power of 2, that is 4, and the largest power of 5, 25, and we can combine those to get z100. We proved that just a few slides ago. So we have z100 from these two cross z2. Here's what we get. I label this one in purple because it's got a red factor and a blue factor. And now we can't do anything with this 2. The GCD of 10 and 2 is not 1, so we cannot combine further. Let's keep going. z2 cross z2 cross z2 cross z25. Let's take the largest power of 2 and the largest power of 25. That gets us z50, and then we have a z2 cross z2 after that. So z50 cross z2 cross z2. And again, none of these are pairwise relatively prime, so we're done. Next, z8 cross z5 cross z5. Let's take the largest power of 8 and the largest power of 5. That gives us z40, and then cross z5. So z40 is in purple, and then z5 is left over. Next, z4 cross z2 cross z5 cross z5. We take the largest power of 2, that is 4, with the largest power of 5, which is 5, and we can combine those to get z20, and then we have left over z2 cross z5. But those are relatively prime. We can combine those. 2 and 5, 2 times 5 is 10, so we can get a z20 cross a z10. And so I'm writing both of those in purple because they both have red and blue factors. Finally, z2 cross z2 cross z2 cross z5 cross z5. We take the largest power of 2 with the largest power of 5. That gives us a z10. And then with what's left over, take the largest power of 2 with the largest power of 5. That's also z10. And then we have a z2 left over. So this group is isomorphic to z10 cross z10 cross z2. Hopefully, it was clear from my greedy algorithm of how I was combining the highest powers of 2 with the highest powers of 5 iteratively, why each one of these indices over here is a multiple of all of the indices directly to the right of it. And that's what the elementary divisor characterization says. Each ki is a multiple of the successive ki plus 1. Now, just for fun, I want to finish this lecture by showing you the classification theorem for all finitely generated abelian groups. Not just finite abelian groups, but finitely generated. And as we'll see, it's not much different. Before I show it to you, let me emphasize what I mean by finitely generated versus finite. So Z10 is a finite abelian group, right? Well, Z, the plain old integers, that is not a finite abelian group because it's infinite, but it is finitely generated because it is generated by 1. Well, what are some other finitely generated abelian groups that you can think of that are not finite? Well, how about Z cross Z10? That is not finite, but it is finitely generated. What is it generated by? Well, what about this? What about 1, 0 and 0, 1? That will obviously generate. Now, these 1s are different because this one is taken modulo 10, and this is just a plain old integer. Okay, so now the theorem. Every finitely generated abelian group A is isomorphic to a direct product of cyclic groups, same as before. In other words, for some integers n1 up to nm, A is isomorphic to a direct product of k copies of the infinite cyclic group Z. Note that Z is infinite and cyclic. And then some number of copies of finite abelian groups. And here we can assume that each ni is a prime power. In other words, it is pi to the di, just as before. Or if you prefer, you can restate this theorem in the elementary divisor language so that each one of these numbers is a multiple of the next one. In other words, A has the following group presentation, generated by A1 up to AK, corresponding to the generators of these, and R1 up to Rm, corresponding to the generators of these, subject to these relations. Now let me point out, this is important, that in writing it this way, with exponents and multiplication, I am implicitly assuming that we are using multiplicative notation for the group. However, how I've written it up here, this is more common, we're assuming additive notation. That doesn't matter too much. You can think of these zi's as a ci instead. And the z's, the integers, well, we don't really have a notation that we've been using for an infinite cyclic group. I guess we could call it C infinity, but Z is more common. I guess when we were looking at freeze groups, we had a few of those that were infinite cyclic, but we didn't give it its own notation. But that doesn't matter. All you should remember is that these are the generators, R1 up to Rm. Each of those are generators of finite cyclic groups. So we need the relation that Ri to the Ni is equal to 1. And A1 up to Ak, each of these generate infinite cyclic groups. So there is no relation. There is no power of Ai that will ever get back to the identity. And so this is the group presentation for a group like this, just in multiplicative notation. In summary of this entire lecture, abelian groups are relatively easy to understand. In contrast, non-abelian groups are more mysterious and complicated. They don't necessarily have Cayley diagrams that can be arranged in nice, neat grids. Soon, we will study the CELO theorems, which will help us better understand the structure of finite non-abelian groups.